Hello and welcome back. We're at section 3. We're going to talk about rates of change, in particular velocity and marginals. Velocity, you should recognize that's about the same thing as speed. Marginals, that's different, but it has to do with business basically. And we'll get to that. So what are we going to talk about? Average rates of change of functions over intervals. Notice a couple of things about this. First of all, get this pen going here. The two things I particularly want you to recognize is average is talking about intervals and changing of functions. So you're talking about going from one value of y to another value of y over an interval. An interval means you're going from one x value to another x value. So keep that in mind. Now, we're not talking about derivatives. So this is a little bit different, so be careful. We are going to talk about instantaneous rates of change. That's where we use the derivatives. We need limits for that. That's because we're talking about what's happening at a point or points. This one talks about intervals, so keep those straight. Average has intervals. Instantaneous has points, not intervals. And last of all here, we're talking about marginal values, revenues, costs, and profits. Good news is, all you have to do is know how one works, and you've got all three. Trust me. Get one down, and you've got all three down. It's a 3-for-1 deal. So average rate of change. So remember I said about intervals? Here's the interval. A to a plus h is an interval, and from this value of y to that value of y. Average rate of change. Got 2 points, 2 x values, 2 y values. You've already talked about 2 primary applications of derivatives. Excuse me a second here, I have to make, there we go. There's something in my way of seeing what you see. There we go. So one of those primary applications we've talked about in the past is slope. And when we talk about slope in calculus, we can talk about the derivatives of particular functions. It's a function that gives a slope of f. Here's the initial function that you're interested in, and the slope is actually a derivative. It's a function itself. Here's the function, and the derivative, or the slope, is f prime of x. The f comes first, the f prime second. Also, slope, rates of change. Somewhat the same thing, really. And it can be changes of all kinds. Quite often, it's with respect to t. X in general, t quite often. So average rate of change, how do we do this? Well, there are quite a few applications of this rate of change things. Velocity, acceleration, population growth rates, unemployment, and so on. But they all, quite often, they change with respect to time. But you can talk about changing with respect to any related variable, not just time. We'll get to that in time though, excuse the pun. So when you want to find that rate of change, you have to be careful to distinguish between average, that's over an interval, and instantaneous is at a point. So think of taking a trip from here to, say, Washington, D.C. If you check the time and the distance, or the odometer reading before you start, and check it again when you're finished along with the time. You can find your average speed. The average speed. If you know what you have to begin with, what you end up with in terms of where you are with your odometer, and what the time is, when you start, when you end. Instantaneous means, suppose we're going through Charlotte on our way to Washington, D.C. As you pass the middle of Charlotte, you've got a certain instantaneous rate of change. That's what you see on your speedometer. So take special notice of the distinction between these two. The average one is talking about the slope of a secant line through 2 points. And the other is talking about the slope of a tangent line at 1 point. So you've got secant line versus tangent line, 2 points versus 1 point. This for the average. I guess I didn't do that well. There's for the average, for the secant line, and this one is for instantaneous. We'll just shorten that a little bit. So here's what we mean about average rate of change. You've got 2 points. A, f of A, B, f of B. Now remember, f of A just means what's the y value at an x value of A. What's the value of y at an x value of B. The x value goes from an A to someplace B. Next, one application is average velocity, like taking a trip from here to Washington, D.C., for example. How far did you go? How long did it take you to get there? That will give you the average velocity. It doesn't tell you how fast you're going when you go through the middle of Charlotte or go through the middle of Richmond, Virginia, for example. This is the average for the entire trip from the interval of, say, 5 in the morning to sometime in the afternoon. Some examples might help here. So let's talk about a free-falling object. So here's a cliff, and we're going to put you at the top. There you are. And what you're going to do is you're going to drop a stone off the edge of the cliff. That stone is a free-falling object because there's no outside forces other than gravity acting on that. We're going to ignore air resistance, by the way. Now, it says here, if you drop it from a height of 100 feet, so we're talking about maybe 100 feet here. The height at any particular point at a time t, we're talking about seconds because it doesn't take long to drop 100 feet. You can find out where that object is by using this formula. S represents the distance, and t represents the elapsed time. How long is it since you left go of the stone? And 100 over here represents how high you were from the ground down here. How far is it from where you dropped it all the way down till it hits at the bottom? Now we're going to take a look at 3 intervals. We're going to go from 1 second to 2 seconds, from 1 second to 1.5 seconds, and 1 second to 1.1 second. Notice we're sort of sneaking up on 1. So what do we have here? Okay, let's get this picture back in. You've dropped the stone here, and the distance from there to where it hits at the bottom is 100 feet. And you're dropping it, we're going to call that time 0. No time has gone by until you start the stopwatch. So this first one means, okay, we just barely started the stopwatch. It's 100 feet in the air. What does the second one mean? It means 1 second has gone by and the stone is still 84 feet in the air. The third one means 1.1 second has gone by, and this is where the stone is, 80.64 feet above that ground. Next one, the stone has been traveling for 1.5 seconds, and it's 64 feet above the ground. And last of all, I hate to belabor this, but I want to make sure you get this point. This means the rock has been, or stone has been falling for 2 seconds. Right now, it's 36 feet above the earth or above the ground. So for this particular one, the stone has been falling for 2 seconds. Somewhere in here, 2 seconds have gone by since the stone was dropped, and it's still 36 feet from here to the ground where it's going to hit. Here's how we find average velocity. We're talking about the time interval here from time equals 1 to time equals 2 seconds. So those are the values, the ends of the interval, and those go in the denominator. 2 minus 1. And what we've got from the table up here is at 2 seconds, it was at 36 feet above the ground. At the 1 second point, it was 84 feet above the ground. So what's the average velocity between 2 and 1 second? We'll subtract the distance values, 36 minus 84, and 2 minus 1. The bottom is pretty easy, right? So 1 in the bottom. Notice this is negative. Negative. So what is it? Let's see, 48 feet. And down here, how many seconds have gone by? 1 second. So the average velocity between the 2 second point and the 1 second point is negative 48 feet per second. Now that doesn't mean it was going that speed when it got to 1 second or when it got to 2 seconds. That means its average speed over that interval. So obviously, when it hit the 84 mark, it wasn't going as fast. 1 second later, it's going a lot faster when it hits the 36 foot mark. And we've obliterated that. We can get that back. We'll erase that ink so you can see it. That's the average speed in going from the 1 second mark to the 2 second mark, in going from 84 feet above the ground to 36 feet above the ground. There's our average velocity. Could write it this way perhaps. Average velocity. Now let's try this again for a different interval, from 1 to 1.5 instead of 1 to 2. So here's the 1 second mark and the 1.5 second mark. Just put those numbers in. Remember, the time goes in the bottom. So 1.5, that's where we stopped our interval. Here, the 1 is where we started the interval, and then match those up here. Make sure these match. The 64 and the 1.5 go together, and the 84 and the 1. Take a look at the table up here. See what I mean? Distance is on the top, time's on the bottom. Subtracting both. So do a little bit of that subtraction, a little bit of division, and that's the average speed in the interval 1 second to 1.5 seconds after the stone has been dropped. If we want to take another one, say from 1 second to 1.1 second, here we've got, there's the 1 second mark, there's the 1.1 second mark, just a little bit past that 1 second mark. Here are the numbers you can get directly from the table. A little bit of arithmetic here. And your average velocity from 1 to 1.1 second is negative 33.6 feet per second. Now, you might not have noticed, but these have negative values. The speed is negative. Why is that? Because a distance downward is considered a negative distance. So the velocity, of course, would be a negative value because it's going downward. Now, how about the instantaneous rate of change in velocity? Well, that's a different story. We're talking about one point in time. How fast is it going then? That's like what your speedometer says in the car versus the average rate of change over some kind of time interval. So if we want the speed at t equals 1 second, in other words, we drop the stone, 1 second later, if we could freeze everything in the whole universe and take a look, how fast would that stone have been traveling? Well, we can use that formula we had before. Remember the formula? S equals negative 16 t squared plus 100. This will give us the distances. S represents distance, quite often in physics and related subjects. We can use that formula to get these values. 1 second, half a second, 0.1 second, and so on, until we get down here. Gee, I wonder what the speed was at 0 seconds when we first let go of the ball. Well, here are the values you can get from delta S, delta T. The T values you can get from this formula. Just put the associated values in here, and you can find out how the speed or velocity is changing. Notice that the speed, as we drop this delta t smaller and smaller, this delta S, delta t, as we get the interval smaller and smaller, we get closer to that value of negative 32 for the speed. So here's the instantaneous rate of change. Now, the instantaneous rate of change, if you want to compare that with speed, the top is like distance, the bottom is like time. Now, those aren't always the case, but this is a good example to learn from. If it is distance and time, then we're talking velocity, instantaneous rate of change. Here's the general position function. In fact, I would add just a slight bit here, because this S hot here would be the final position of whatever that object is. This is the initial position. Where is it when you dropped it? This is how fast it was going when you let go of it, and this represents where it is at a certain time in the future. Remember, positive velocities mean you're going upward. Negative velocities represent downward motion. Many of you have taken physics or something similar in the past, so this should be a little bit familiar to you. Now here's another way of using the word derivative. We start with the position function, that was s, remember? And by taking the derivative, we get the velocity function. And here's the velocity function. Remember, this isn't s, this is s prime, which means ds dt. And that velocity function is negative 32t. That's the elapsed time, how fast is it going after that time has gone by, plus how fast was it going to begin with when you started the stopwatch. Velocity represents how fast it's going in a particular direction. Speed means just the speed of it alone, without considering the direction. Let's take a look at a diver off the diving board. Here's a picture of the diver. Now, if you picture a diver without looking at this picture, you know they actually start going upward to bounce off of the diving board, and then a short time later they're headed toward the water, and the water would be like distance equals 0 or ground 0. Here's the position function. There's a negative 16, and there's the initial velocity, and there's where the diver is when he takes off. He's 32 feet above the water. We want to find out when does the diver hit the water. We also want to find out how fast he's going, or his velocity at impact. Obviously he's going downward, so that part of velocity we do know. We don't know what the magnitude is. Direction, yes. Magnitude, not so much so far. So how can we do that? Well, first of all, we're going to start with the position function. And since we want to know when he hits the water, that's when the distance, his distance above the water is 0. He's hitting the water. So we take that s equals negative 16t squared plus 16t plus 32 equals, and we'll set that equals 0. He's hitting the water right that instant. So putting that 0 in, we've got a quadratic equation. Remember I mentioned about the quadratic equations? Two things you ought to know. First of all, you can use the quadratic formula to solve that. Second, you can also, if possible, use factoring to solve that as well. So we can factor out the negative 16, so we can ignore the 16. If you look at this, we've got two numbers being multiplied together, the negative 16 and this expression. Now the zero factor property says if I multiply those two numbers together, I get a 0. Well, obviously the negative 16 isn't 0, it's negative 16. So we can basically forget about that. We know that one of these two, after factoring, one of these is 0. So set them equal to 0, solve for t. Now what does the t represent? Remember, that's how long the diver was in the air until he got to a certain point. So this would represent 1 second before he took off. Well, that's worthless. This one says time equals 2 seconds after he took off. So since this one doesn't make any sense, we can't go back in time. Our answer is 2 seconds after he took off, he'll hit the water. How about the velocity? Well, we've already got that, remember? This is the same thing as ds dt because we're talking about time. And here's our formula. What do we want to find out? Well, we want to find out what this velocity is when he hits the water. When did he hit the water? We just found out. 2 seconds after he took off. So all we have to do is take that 2, put it in for t. So t equals 2. There we go. Substitute. And that's how fast he's going when he hits the water. Negative 48 feet per second. The negative means he was going downward, obviously. And 48 feet per second. Pretty fast. So notice that the diver's initial velocity, that's what this represents, the 16 part that is. That's how fast the diver was going when they started the stopwatch. Since it's a positive 16, that means the diver took off upward. Of course, that's what happens, right? And he's going upward at 16 feet per second as you start the stopwatch. 32 means how high he was. And this part here has to do with gravity working. If we were actually on the moon, some of this would be different. This part right here would be different. Now we get to the marginals. We're talking about economics, and as I quote, warned you, unquote, this is going to be pretty easy. We're talking about marginals, and that means we're talking derivatives. How are things changing? That's what we're interested in. Economists refer to marginal profit, marginal revenue, and marginal cost. Get one of those down and you'll be in good shape. Remember, cost is how much it costs you to make something. Marginal revenue is how much money is coming in, and marginal profit is how much you get to use toward going to some special place for a vacation at the end of the year. So what this represents, the marginal values, are how things are changing. The profit, revenue, or cost with respect to X. Quite often time, but it could be something else. And it's the number of units produced or sold. And that's what X represents. So here's a basic equation you need to either memorize or write it down somewhere until you can't forget it anymore. It's quite obvious, really. If you think of profit, well, how do you get a profit? Well, you sell something, you get some money in. But then you have to pay the bills first, the cost. What's left is your profit. Profit equals revenue minus cost. We'll use that all semester long. Also remember that the P, R, and C, profit, revenue, and cost, refer to total profit, total revenue, and total cost. It might be obvious, but if not, keep that in mind. The derivatives of those, so you're starting with P equals R minus C, profit equals revenue minus cost. The marginal profit is P prime. Also, you could write as dP dx. X is the number of items. For marginal revenue, R prime. You could call that dr dx. How much is the revenue changing, up or down, every time you increase your sales by one item? And cost, C prime, dC dx. How does your cost change per item as you sell more of those TVs or whatever it is you're selling? There's marginal profit, marginal revenue, marginal cost. Notice how very similar all those three are. Again, one more time. If you can get this one down or any of the others, the other two will follow very quickly. Now, one thing to keep in mind is that quite often the number of units you produce or sold are integers, positive integers, or non-negative actually, because you could have 0. However, for our purposes, we could sort of interpolate or imagine other possible numbers in between. You can't very likely sell the square root of 2 TVs, for example, but you could imagine this as a math thing. You could imagine it being a continuous function. One that has integer values like this, or non-negative integer values, are called discrete variables. In other words, they come in chunks. It's sort of like going to the store and deciding you're going to buy flour. Well, you could go to a store that has bulk items. You can get any value you want. But at a typical grocery store, you get a 1 pound bag, 2 pound bag, 3 pound bag, 5 pound bag, 10 pound bag, and so on. They come in units or chunks. Those are discrete variables. So to analyze these discrete variables, we're going to assume that they're continuous because we've got a lot more tools on continuous variables than we do for discrete. So this is what it will look like if we smoothed in the curve. So let's get back to the marginals. We're going to use calculus to find the marginal revenue, marginal profit, marginal cost, or whatever we need. When you get it, if it's a discrete variable, remember to round to the nearest reasonable x value. It might be round to the cents, dollars, units, days, whatever the problem calls for. So here we've got an example to play with. Finally, right? So we're talking about profit. Remember, that's total profit. Just a little bit of a reminder here. The total profit in dollars, not thousands of dollars, just dollars, from selling X units of an alarm clock. Here's our function. Now, if you're a real math person, you probably want to think of it in terms of a function, because it's a function of X. But that's a technicality. First of all, you want to find the marginal profit at production level of 50. So we'll get the marginal profit. We put the 50 in to see how the profit is changing when you go from 50 to 51 units. Or in this case, from 50 alarm clocks to 51 alarm clocks. How many more dollars do you get by selling one more than you did last month? Then we're going to, now this is using calculus, and we'll get a good estimate. Second of all, what we're going to do just for practice and to see what the difference is, we're going to compare that marginal profit with the actual change in profit. Because at 50 units, 50 alarm clocks, when you go to 51 alarm clocks, one more alarm clock, you're going to get a certain amount more profit. Well, there's an exact value. Up here, you're getting an approximate value. It'll be close, but not exactly the same necessarily. So here we go. We've got a profit function from above. You can check it up there to make sure there are no typos. The marginal profit is the derivative of the profit function. There's the derivative. Remember, bring the 3 out front, multiply it times the 0.0002, so you get 0.0006, and the x cubed becomes an x squared. On this one, you just got 10x. If you want to, you can say there's a 1 there. 1 times 10 is 10, and x to the 0 is 1. So it's just a 10. When you have something like that, if, for example, you had a function like g of x, remember, and let's suppose it's negative 3x, and your derivative for that simple one is just the negative 3. Moving along. So here is our, if you look back here for a second, you might want to write this down because I don't have it copied. There's our marginal profit function, our derivative. If you take this, and we want to find out what the marginal profit is at a level of 50. In other words, at 50 alarm clocks, what can we expect as extra or less profit going from 50 to 51 alarm clocks? So all you need to do is put the x value in for the x in the marginal profit function and do a bit of calculation. So this tells us, using a small bit of calculus, that if we go from 50 alarm clocks to 51 alarm clocks, we're going to get an additional $11.50 per alarm clock by increasing our production by 1. Now, the second part is, we've just gotten an estimate, $11.50. That should be good enough for us, but let's see how close it is. So we'll put the 50 in here. This is going to tell us what the actual profit is for 50 alarm clocks. Do a little bit of arithmetic. So if we're selling 50 alarm clocks, we get $525 of profit. What about one more? We'll just go back here, and instead of 50, we'll put in 51 instead. See what happens. So put the 51 in. A little bit of arithmetic. So if we sell 51 alarm clocks, we make $536.53 exactly. So what's the difference? Subtract those two. You've gotten an additional $11.53. Now that's the exact, because we use the profit function for that. Using the marginal profit, remember we got $11.50. Pretty close. And usually that's as close as we'll need for our business application. And there you've got a picture of everything. We're going from 50 alarm clocks to 51. Profit is going up by $11.53. Here's our graph, and there's our marginal profit according to our model. Now what you'll notice back here on that picture is that this model is a linear one. So it's a line. However, that's usually not the way it works. Usually you don't continue to increase your profit just by selling some more alarm clocks or whatever it is. Usually what does happen is that the only way your sales go up is you lower the price per item, but that changes your profit too. So this is very idealistic. And usually the profit will go down if you're reducing the price. Less money coming in, even though you will sell more. Now here's something that could be confusing if you're not careful, so be careful. This is called the demand function. And quite often you'll see it written like this. But what you've got is, this is the price per unit. And it depends on how many items you actually sell, what price you can put on it. Also notice this is another one. Here's your price that you got up here from the demand function. If we want the revenue function, all you need to do is take the price, multiply it by how many items you're selling, and that's how much money is coming in. Also called the revenue function. Revenue equals number of items times the price per item. So we're going to a fast food restaurant and take a look at things. Here's our demand function. Remember, it starts with P, even though it's a demand function. You might think it's a price function, but you'll have to talk with the economists about that. So here's our demand function, and this is number of hamburgers, or actually straight number. This is how many hamburgers you're actually selling. You can see that if you graph this, this is how it goes. The more hamburgers you sell, the lower the price is. That's how you do it. If you put these into a table, you can see how this is working. With 60,000, if you want to sell 60,000 of these hamburgers, you're going to have to give them away. If you want to sell 50,000 of the hamburgers, charge 50 cents each. One more. If you want to sell 20,000 hamburgers, you'll have to charge $2 for each one. And if you charge $3, you can expect to sell 0. So put the number of hamburgers in here for X, and you'll find what price you need to establish to get that kind of sales. Now, this is the function we showed just a little bit earlier. That's the demand function. If you want the revenue function, just multiply it by X, and there you've got your revenue function, which will look like that. There's your X, and there's your P, from the demand function. Simplify it a little bit, it might be easier to use this. If you want the marginal profit, differentiate this function right here at the bottom. There we go. There's our function. Differentiate that, and there we've got our derivative, or our marginal revenue. So if you want to know what the price needs to be to sell 20,000 hamburgers, just put the 20,000 in where the X is and crank away with some arithmetic. So you have to charge $1 per hamburger to be able to sell 20,000 hamburgers. Well, here's an extra function. We've got a total cost function. This is the cost of everything. Now, you can pull this apart and you can learn some things just by looking at this one line. First of all, this part in here says you're not going to sell negative hamburgers. That's pretty silly, right? And for whatever reason, you're not going to be able to sell more than 50,000. If you looked at that graph we had, or the table, it shows you that if you extend that and sell more than 50,000 hamburgers, you're going to have to be giving them away. Well, that doesn't make any sense. So X has a value from 0 to 50,000. That's the domain of the X, or the number of hamburgers. Here's the cost function. Now this cost function also tells you something too. If you sell even 0 hamburgers, you're still going to have to pay $5,000, perhaps for the rent of your hamburger place, maybe for insurance. There are a lot of things that are possible. The air conditioning, for example. So your total cost will be that $5,000, and then your cost is going to go up by 56 cents for every hamburger you decide to sell. Now here's something for you to try. You might try pausing the video and see if you can figure out the profit and marginal profit for each production. So, from example 7 that we already talked about, here's the revenue function. And the total revenue for selling X hamburgers, there's our X, here and here. Put the X you're interested in, and you can find out what the revenue would be from selling X hamburgers. Excuse me. Since the total profit is revenue minus cost, and we've already got the revenue function, and we've got the cost function, revenue minus cost, what's left? The profit. So you can actually do this with your algebra and find out what the profit function is. A little bit of simplification. Music, please. There's your profit function. 2.44x. Remember, x represents the number of hamburgers here and here, and that 5,000 is constant. You're always going to be paying out the 5,000. So the marginal profit is put the value in for the number of hamburgers you're interested in. So for 20,000 hamburgers, you're going to have a marginal profit of 44 cents per hamburger. That means if last month you sold 20,000 hamburgers, and next month you're going to sell 20,001, you're going to have an additional 44 cents of profit. At this level of selling hamburgers, this will be your total profit, and this is how the profit is increasing as you go from 20,000 to one more hamburger. Next, if this is how many hamburgers you're selling per month, where's my cursor here? Oh, there we go. Okay, sorry. So if you're selling 24,400 hamburgers this month and decide you're going to sell one more next month, you're not going to make any more money. That should tell you something. At that level, selling more hamburgers is not going to help you get more profit. At 30,000, look what happens. If you're selling 30,000 this month, what happens if you sell more hamburgers? Well, for every hamburger you sell beyond 30,000, you're going to be losing 56 cents. So you should be able to see why you need to know about marginal profit, marginal revenue, marginal cost. This tells you where to stop increasing your sales and take your profit and run, so to speak. Okay, well that's about it for section 4.3 on velocity and on marginals. See you next time when we'll get to products and quotients when we're taking derivatives. Till then, you take care. Bye. Goodbye.